Good morning. In last lecture, we have stopped in operation of PN junction and forward bias. So I'm just recalling it and starting it again. So to understand the working of PN junction diode, we consider two effects in the PN junction. One is forward bias and the other one is reverse bias. So forward bias, as I said earlier, when the external voltage, the external source, that is a battery, positive is connected to P-type semiconductor and battery negative is connected to N-type semiconductor. It is termed as forward bias, and it has been explained here. The diagram, from the diagram you can understand it. So when external voltage is applied to the PN junction, the potential barrier is cancelled or eliminated. So external voltage is applied with the help of external source, that is nothing but the battery. So as the potential barrier is eliminated or cancelled, it will permit the current flow. So as the potential barrier is eliminated, the resistance will decrease and make the current to flow into the circuit. And this process of eliminating the potential barrier and permitting the current to flow is termed as biasing. And forward bias, and this I said earlier, forward bias is defined as and the positive terminal of the battery is connected to P-type semiconductor and negative terminal of the battery is connected to N-type semiconductor. And by this process, the potential barrier is reduced and by the forward voltage, and the junction establishes a low resistance. As I said earlier, barrier voltage is get reduced and the junction resistance is also reduced and current flows to the circuit, and this current is termed as forward current. And coming to reverse bias, it is just completely opposite to what we have seen in forward bias. From the diagram itself we can understand. Here the battery positive is connected to N-type and battery negative is connected to P-type. So the operation is going to happen in the reverse way. That is why it is termed as reverse bias. And in this process, when external voltage is applied, the barrier voltage gets increasing, whereas in forward bias the barrier voltage is reduced. Here the barrier voltage is increased, and as the barrier voltage increases, the depletion region will increase. So as the depletion region will increase, and as the barrier voltage increases, the barrier width will also get increased. So this will in turn establish very high resistance path. So as there is high resistance, no current can flow through the circuit. Although a few amount of small amount of current will flow through the circuit due to minority carriers, and this current is termed as reverse saturation current. And if this process goes on continue, the junction breakdown will occur. As the barrier voltage goes on increasing and the barrier width goes on increasing, there will occur a breakdown, and the junction and it is termed as junction breakdown. And thus the PN junction diode will offer a very low resistance when it is going to act as a conductor during forward bias, and a very high resistance and will act as an insulator during reverse bias. And coming to voltage and current characteristics of PN junction diode, I have shown the diagram for VA characteristics of the PN junction diode, and it is been shown for both germanium as well as silicon at both forward bias region and the reverse bias region. So we can, from the diagram itself, we can understand the breakdown voltage or the threshold voltage will occur for germanium at 0.3 volt and for silicon at 0.7 volt in the forward bias condition. And this change in, that is the point where the change in forward voltage occurs is mentioned here, and the change in forward current is also mentioned here. So the forward resistance is diode resistance is given by the ratio of change in forward voltage to the change in forward current. Similarly, for the reverse resistance, it is nothing but change in reverse voltage to the change in reverse current. And the diagram shows for both forward as well as reverse bias. And here for the reverse bias, the silicon voltage happens in the reverse manner, and the potential barrier goes on increasing. So one more thing what we understand from the figure is the point AB and A', B' are the linear operating region, that is, it is going to be constant and there is no deviation with the change in current. And because of this region, the depletion layer will disappear. That is, as the potential barrier decreases and get eliminated, the depletion layer will disappear. In forward bias, when the forward voltage is applied, the potential barrier is eliminated and currents flows at one value of voltage, and this value of voltage is nothing but, as I said earlier, it is the threshold voltage. It is termed as VTH or cut-in voltage or knee voltage. And coming to diode resistance, an ideal diode has zero resistance in forward bias and infinite resistance in reverse bias, but in practice it is not ideal one. So the ratio of total voltage and current of volt ampere characteristics to diode gives a static resistance, and it is the reciprocal of the slope of line joining the operating point to origin, whereas the dynamic resistance is the reciprocal of the slope of the VA characteristic. That means it is going to be the ratio of change in voltage to the change in current, whereas static voltage is the total voltage ratio of total voltage to the total current. And application of PN junction diode. This PN junction diode can be used as a switches, and it can also be used as rectifiers. Rectifiers, we use diodes. Those diodes are nothing but PN junction diode. And power supplies also it can be used, and clippers and clampers, digital systems, and also can be used in communication systems. Coming to breakdown mechanism of semiconductor diodes. So when a diode is reverse biased, this operation I have explained before. The junction breakdown, the same thing I am going to repeat here. So when the diode is reverse biased, the depletion layer is wide enough and set up a large potential barrier. That is, the potential barrier width goes on get increasing and increases the resistance and diffusion of majority carriers from one side to other side, and it is going to prevent the diffusion of majority carriers from one side to other side. As I said earlier, diffusion is the process of reducing the barrier voltage, and it makes the current to flow through the diode, whereas here it prevents the diffusion process, and thus there will be no current due to the majority carriers. As the reverse bias is further increased, this reached the point where reverse current suddenly shoot ups. So as the reverse current shoot ups, it causes a breakdown in the junction, and this is termed as junction breakdown. And this junction breakdown mechanism is carried out at two ways. One is Zener breakdown and other one is avalanche breakdown. We can see the definition of Zener and avalanche breakdown. So Zener breakdown, it is going to occur primarily in heavily doped diodes. Heavily doped means a more number of impurities is being added in that particular diode. That is highly conducting diodes, and depletion region is very small. As I said earlier, if impurities were added heavily, the depletion region will become small, and it occurs with a reverse voltage which will be less than or equal to 6 volt. And for lightly doped diodes, Zener voltage will be very high. So breakdown predominantly have to occur through avalanche breakdown. So here itself we can understand one difference between Zener breakdown and avalanche breakdown. It is going to, your Zener breakdown is will occur when it is highly doped, and avalanche breakdown will occur when it is lightly doped. And the same point is here. Avalanche breakdown, it occurs in lightly doped and depletion layer is very wide, and it is going to occur with reverse voltage greater than 6 volt, and the reverse voltage applied in parts will high energy in the minority carriers. So these minority carriers with sufficient energy disrupt the covalent bonds in the crystal. So while disrupting the covalent bond in the crystal, it will release the valence electron, and this process is termed as impact ionization. Okay, and the newly released valence electrons due to impact ionization gain enough energy and disturb the covalent bonds also, and this process will become an uncontrolled chain reaction, and this process will cumulatively it is termed as avalanche multiplication. So by this way your avalanche breakdown will happen. And here I shows the comparison of Zener breakdown and avalanche breakdown. So coming to Zener breakdown, it occurs as a heavily doped junction, whereas avalanche breakdown is going to occur at lightly doped junction. And for Zener breakdown, it occurs with reverse bias voltage less than 6 volt. Here in avalanche breakdown, it is going to occur with reverse voltage greater than 6 volt. And for Zener breakdown, the temperature coefficient will be negative, whereas for avalanche breakdown, temperature coefficient is positive. And for a Zener breakdown, the reverse bias voltage and current characteristic is very sharp in the breakdown region. That is, it forms a sharp difference at the breakdown region, whereas in reverse bias VA characteristics, it is not sharp, it is very soft. And in Zener breakdown, it occurs by breaking covalent bonds. Both Zener breakdown and avalanche breakdown will occur by breaking the covalent bond. But how this covalent bonds are broken is for Zener breakdown, it is broken with due to very high electric field established by reverse bias. Whereas here in avalanche breakdown it occurs due to collision of accelerated electrons. Collision, we all know, collision of accelerated electrons as a chain reaction, that is as we have seen earlier, avalanche multiplication. And coming to Zener breakdown, the breakdown voltage decreases if the junction temperature increases. So if we increase the junction temperature, the breakdown voltage will decrease, whereas in avalanche breakdown, if we increase the junction temperature, the breakdown voltage will also increase. So this shows the comparison of your Zener breakdown and avalanche breakdown. Coming to Zener diode. So in general, the purpose of PN diode, the doping is light. Generally, the PN diode, the doping will be very light. That means the impurities added will be very small. As a result, the breakdown voltage will be high. So as the impurities, if we add very low number of impurities, the breakdown voltage will be very high, and the P and N region or heavy, if P and N region are heavily doped, the breakdown voltage will be reduced. So that means as the breakdown voltage reduces, the breakdown voltage is also called as barrier voltage. As it reduces, the current will flow into the circuit. So when only if we heavily dope, that is only if we add impurities at a high level, your breakdown voltage will be reduced. So when doping is heavy, even if reverse voltage is low, the electric field at the barrier is so strong, and electrons in the covalent bonds can break away. So even if the reverse voltage is low, when it is heavily doped, the covalent bonds will break away. So this is termed as breakdown, Zener breakdown, and this effect is known as Zener effect. So the diode which is going to exhibit the Zener effect is termed as Zener diode. So Zener diode is defined as the reverse biased heavily doped PN junction diode which operates in the breakdown junction. That is, when a heavily doped PN junction diode operates at the breakdown region, it is termed as Zener diode. The Zener diode has been designed to operate the voltage ranges from few to several hundred volts. It can operate from 2 to several hundred volts. And here I show the equivalent circuit of the Zener diode. And here it is a simple diode format, that is it has a cathode as well as anode. And in actual case, how your Zener diode looks like is, it is going to have a voltage source which is going to produce the Zener voltage Vz and Zener resistance Rz. And in ideal case, it is going to be only a voltage source which has positive and negative terminals. And these are the symbolic representation of your Zener diode and its equivalent circuit. Coming to VI characteristics, that is voltage and current characteristics of Zener diode. This is a graph drawn between voltage and current, both in forward bias as well as reverse bias. So as the operation happens in reverse bias, we see when it reaches the threshold voltage, your voltage becomes constant, reverse voltage becomes constant, and this approximately the midpoint between the maximum Zener current and minimum Zener current, there occurs a Zener voltage, and it is termed as Vz. That is what I have explained in words, that the voltage across the terminals of the diode for a current Iz, which is the approximate midpoint of the linear range. That is when it becomes constant. Linear range of the reverse characteristic is called as Zener voltage. And coming to applications of Zener diode, it has been used as voltage regulators, as the key clippers, and for reshaping the waveforms we can use Zener diodes, and also for the protection of meter against damage from accidental applications of excessive voltage. So when excessive voltage applications accidentally occurs in a meter, in order to protect that we use Zener diode. And here I end up this lecture. Thank you.